Hi, thanks everyone. So I am Reyha Verma. I will be talking about from notes to codes. I'll try to walk you through how you can build a efficient medical coding pipeline using Python today. So in the meantime, maybe you can open the slides if you're interested. There might be a few slides that have some content in the bottom, which might not be visible. So yeah, I am Reha. I'm currently an applied scientist at Amazon. I have previously worked in companies like Arintra, PayPal, and Sprinkler. So the work that I did in Arintra, which is sort of automating medical coding, is something I'm also trying to present here today. So the agenda of this talk is that I'll start by introducing what medical coding is, just to set some context, and tell you why is it important to code accurately, and also touch base on why is manual medical coding complex, and why is there a need of automation in the first place. Having said that, I also want to walk you through the approaches to automate medical coding, and also maybe tell you if there is a best way to automate medical coding or not, and additionally discuss the future directions of this work. So just starting with, setting some context for what medical coding is. So let's say there's Ben who, gets an abdominal pain and wants to go to a hospital. So he goes to the hospital, gets himself admitted, and their doctors come and they do some physical examination and run a few tests. And then doctor comes and looks at those reports and diagnose Ben with acute appendicitis. They also prescribe some medications after keeping him for under observation for a few days. What happens here is that they update his medical records with diagnosis and procedures, whatever was done in the hospital during his entire duration of stay. After a few days, hopefully Ben gets discharged and he is back home happy and healthy. Right? So this is essentially what happens when a patient visits a hospital and comes back home. But there's a lot more that happens in the hospital and in the back end. So I just want to focus a little more on the part where the doctor and the hospital updates the patient's medical records. So what happens here is that a doctor would just write a full form of what the discharge summary was, or what all tests were conducted in natural text form. And there would be a team of clinical coders who would be sitting in the hospital, and they would convert everything that the doctors wrote to clinical codes, which are basically in some standard guidelines, right? So today, US follows ICD guidelines. So this code that you see on the screen here on the right is basically a set of clinical codes. For example, 569.83 is a code for perforation of intestines, and there are similar codes like that. So ICD is basically a set of codes that are used for diagnosis, and CPT are a set of codes that are used for procedures normally conducted. So you might hear me talk about say ICD and CPT during the presentation. So it just means sets of codes that are used for assigning codes to different conditions and procedures. So yeah, this is essentially the process of coding the patient's charts, which essentially more or less is being done manually today. Now coming to the big question, right? Why is it even important to code accurately? So I'll also just walk you through what happens regarding the finances, who is paying for what, and why is it important for us to look at medical codes and to be able to code accurately. So when Ben visited the hospital, he paid some initial deductible, maybe or maybe not. It could also just be a free admission. Then in the hospital, a team of medical coders would then convert the charts to codes, and then they would send that to the company that Ben has his insurance for. So then the insurer would pay hospital once the medical codes that were converted by the team, and they would validate those codes against Ben's policy's cover. If the policy cover covers all the codes that are there in the the chart that the team sent, the insurer would be paying the hospital. If not, if something is out of policy cover, then Ben has to pay that out of his pocket. So this is how the cycle of payments work. Now, the most important part of this entire cycle is essentially the quality of the clinical codes, because that determines how much money should the insurer pay to the hospital, or how much money has to pay to the hospital, right? So it is really important, and it is a big loop because there are 3 parties involved, and it can take a lot of time if something goes wrong in coding those charts correctly or incorrectly. Now, I also want to touch base on why is medical coding complex. It is mostly because the code sets that I talked about, the ICDs, they are very huge. So ICD-10 today contains more than 70,000 codes. ICD-9 has a lot of rare codes, so there are different ICD categories as well, and they keep changing. Additionally, the charts that the doctors write, those are notational, lengthy, and often incomplete. There's a lot of note bloat, so the average number of words are around 1,500. And also, additionally, there's a lot of dependency on the past records. For example, if Ben is coming in today, what I code or a medical coder code also depends on his past history or whatever issues or diseases he has in the past. So it's really a culmination of all the documents and all the medical records of a patient. And the records we know are not always very properly structured and are often missing or incomplete. Lastly, the evolving standards, like I talked about. So the guidelines are evolving and they are very nuanced. There are subtle changes. And there's a lot of clinical nuance that is required to be able to code correctly and efficiently. Coming down to why is there a need for automation, we know that there are manual coders sitting in the hospitals doing this coding. Having said that, so there are stats that say that 20 to 30% of the records today contain coding errors, which leads to delay in reimbursements, compliance risk, and massive administrative overhead. Additionally, there's a backlog of unprocessed claims. So there are around millions of records that are not getting processed in time. So it negatively impacts the entire cycle from provider revenue to patient care continuity, which can result into a lot of issues for both hospitals as well as patients. Also, just a stat here that a clinical coder in NHS usually codes 60 cases per day. And so it's almost like 20,000 cases per month. But still, there is like a lot of backlog that is to be coded, which can take up to months and often like years, which is really huge. And there is a definite need of automation here. So this is where AI definitely can play a transformative role. And this is what I also want to talk about today. So there are different approaches that the community has taken over years to solve the problem of medical coding. So starting with very fundamental symbolic rule and knowledge-based approaches. The idea here is that we know that you could have a KB and you could have very simple rules to be able to convert the conditions to different codes. It's easier to implement, but the problem is scalability. How do you do it for different healthcare providers? And it is often very time-consuming to even construct those rules. Then the community moved to ML-based approaches where decision trees and neural networks were starting to be used. It is scalable and it is capable of handling complex inputs. However, there's a lack of explainability and there is no support for rare or zero-shot codes. We know that with ML methods, what you give in, you get, right? So if there is no certain code in the training data, you would not get it in prediction ever. Then there are also approaches like knowledge-augmented ML-based approaches where you incorporate knowledge graphs into deep learning. This is slightly better because it helps in zero-shot reasoning and the contextual logic is often included. However, the problem is that as you incorporate knowledge bases with ML, the complexity of the systems generally increase. So today, I want to dig a little deeper into the ML-based approaches and the knowledge-augmented ML-based approaches. Primarily because the world has more or less moved to these approaches and a very few companies or groups are using purely rule-based approaches to solve medical coding. So talking about different ML-based approaches, there are primarily three main approaches. The first one is a multi-label classification approach, wherein you have a single model that predicts a set of codes given a full node. So what essentially this does is you get a full code, you get a full doctor note, and then you, in the end, just get a list of codes. So the beauty is that it's only a single model. It's very easy to maintain that and often like retrain it. But the only problem is that it struggles with long texts, and the explainability part of it is a little problematic. The second approach is the named entity recognition plus linking approach, wherein you extract medical entities first from a doctor's note, and then you link those entities to different codes via ontologies like UMLS. Now, the good thing is that it's often explainable, and it can handle long notes and rare codes. But the problem is that you need context resolution. You often need complex post-processing to consolidate mentions. So it becomes slightly complicated to implement a system like that. And the approach 3 is NERL plus external knowledge base, which basically uses hierarchical rules and ontologies to enhance linking. So it's additionally like what NERL was doing, it's just adding and using those nuanced relationships that already exist in the ontologies to make the coding further better. Now it's really good with zero-shot reasoning because contextual logic is already included. But again, the complexity really increases, and integrating a KB into a production system or to really use across healthcare providers, it remains a challenge. So I also want to go a little deeper into all these approaches and walk you through the different pipelines of implementing these approaches. So talking about approach 1, which is multi-label classification approach. So here the input would be a full clinical note, and the output is essentially the multi-label targets, which is a set of codes per note. So for example, I'm just taking a simple line here for clarity, but often it is a 1500 long, like words long note that you would see in reality. So here I'm taking this example, which is patient with chronic hypertension and type 2 diabetes mellitus, and the labels are I10, E11. These are all ICD-10 codes. So a simple model like clinical BERT or BioBERT, which are already pre-trained on medical data, can be used with the classification head. And you can use evaluation metrics like F1 score, precision recall, depending on what is really important for your use case, and just build a system and automate medical coding using this. You can even further fine-tune the model if you think some codes are missing or you essentially want to add some rules into your model. So the pipeline something looks like this. So you have a node text, you have a model, and then you get codes. So as you can see here, I have used bioclinical BERT here. And then after like some processing, I'm getting these 3 codes, which is not correct because in the last slide that I showed, so the correct code for this condition is just 2. Which means that pre-trained models so this is essentially a black box approach of getting the codes out. So it can often lead to issues, and you might need to retrain or add some post-processing steps to ensure that the system is working really well. So talking about the second approach, which is the named entity recognition linking approach. So here again, the input and the output remains the same. But here, since we are talking of a pipeline, so there are 2 different components here. First one is NER, which is named entity recognition. So there are pre-trained models for that. You can use SPACY, you can use BioBERT and other models as such for NER. Then for linker, you can use SPACY's UMLS entity linker, which is like available off the shelf. And again, here for evaluation metrics, since it is a pipeline, you need to look at both component level quality as well as end-to-end quality of the pipeline. So for NER, you can use span level precision recall, F1 score via sequence match. And for linker, you can use in-KB accuracy, which is basically checking if correct CUIs are present and chosen from the candidate list. And for end-to-end, you can again use F1 precision and recall. Again, just to clarify here, CUI is a concept unique identifier, which is present in the UMLS or the ontologies here. So it's nothing but mapping every entity that you extract to a particular CUI, which again gets mapped to an ICD code. So it's just a way of linking the CPT or ICD to the end outcome. So here, if you look at the pipeline, so it's you enter the node text, then it goes through the NER model, then you have a linker which would link the entities to the CUI, and then there's a CUI to ICD mapping, and then you would get the predicted ICD codes. So here, for brevity, I have just shown these 2 conditions to have this dummy CUI ICD mapping. However, in reality, you can use different dictionaries that are present and ontologies that are present off the shelf. Right? And at the end of it, you would get these 2 predicted codes. Now coming to the third and the most complicated approach, NERL with external knowledge base. So here the input and the output again remains the same. You have NER, you have linker. On top of it, you also have this ontology graph, which is basically trying to understand the relationships between different entities in the UMLS DB. So when I say a relation, there are multiple kinds of relations that exist in the UMLS, or any ontology for that matter. It could be an is a relation, it could be a causes relation. If you look on the right side of the slides, you would see 2 tree-like structures here. So if you closely follow through the chart, I would not go into a lot of detail. This is just to give some idea on how complex it can be. So there is this rel, which is relationship type. It can mean parent, it can be of child type, it can be of broader relationship type. And then there is rela, which is semantic relation type, which means that if rel, basically the relationship type is parent, rela could specify whether the parent is a therapeutic procedure or a finding. And there could be like multiple kinds of rela and rel present in the UMLS. Right, so it's often a culmination of finding relationships between different entities and navigating the UMLS DB using this ontology graph that you can get an accurate ICD. Now coming to the evaluation metrics, so since this is an extension of approach 2, more or less the same evaluation metrics can be used. However, you can also check for ontology correctness, which is basically to check if the predicted CUIs include expected ancestor concepts. So ancestor here means parent and child. This really helps with understanding if your system is capable of reasoning for zero-shot codes and entities or not. Now here, if you look at the pipeline, it starts with the no text. It then goes through an NER model, and then there is a linker. Then it would run an ontology graph where you would get an ICD mapping via the UMLS hierarchy that I just showed. It is often a lot of calls back and forth between UMLS, DB, just trying to understand if the relation makes sense or not. There are some additional steps that are required here. It's not as straightforward as it looks here. But this is more or less what can be used if somebody is interested in implementing an NERL with external KB for medical coding. So the first part of it, you see that I'm just loading an ontology. You can load UMLS, you can have your own ontology, you can maintain your own graphs. Then you have these entities. Here I'm assuming that there are just two entities that are extracted. I'm not running an NER here. And then you basically check the relationships in the ontology and get back the codes. So yeah, just to also make it a little clearer on what is the core difference between NERL and NERL plus KB. So let's say there's a text called patient shows signs of diabetic nephropathy. Here, NERL may only extract diabetic nephropathy and it would give out an ICD of E11.21. This is an end ICD predicted for this particular text. However, NERL plus KB could infer the parent condition. It would tell you this is diabetes mellitus, the parent is diabetes mellitus, which is E11. It would also add a secondary code for chronic kidney diseases, which is N18.3. It would also suggest some monitoring codes based on the rules. So what I'm trying to say here is that it gives you a lot of additional information for a specific condition in your text. And if for your use case, you really need to know that much information, this might be the best approach to use. Now coming to understanding if there is a good way or a best way to automate this process of medical coding. So I have just compared these three approaches on different criteria starting from speed. So speed, multi-level classification, of course, is the fastest because there is just one single model. So we know that once we have trained the model, inferencing a model is pretty easy and you can optimize the models and make it faster. But NERL plus KB, since there are a couple of components that sit within the pipeline, it might be relatively slower. However, you can speed things up if you efficiently design your systems. Coming to the system complexity, like I already said, NERL plus KB is the most complex to implement because there are so many things that you need to take care of. Yeah, and multi-level classification might be the easiest if you have the right data and the right evaluation metrics and the right models, of course. Now coming to accuracy, I think this is something that is really subjective and it really depends on how you implement your system. But often it is shown that NERL plus external KB is the best approach and the most efficient one. Now coming to explainability, again, since NERL uses an external KB, which is an ontology having relationships and hierarchies, it's often easy to explain why a system predicted a certain code. It's really tough to do that with a black box approach like multi-level classification. Talking of scalability, multi-level classification, like we know, it's highly scalable. However, when you want to scale NERL, you might have to do certain optimizations to be able to scale it up for multiple users and healthcare providers, since there also might be some healthcare specific rules that you need to integrate in your pipelines. Now, about rare and unseen code, something that is not maybe present in the training data. Multi-label classification often does a poor job here because we know that we need to give data to model for it to be able to predict the codes. But NERL and external KB can do that because even if, so nothing's getting trained here. So we are not giving any data. We are just relying on an external KB to predict codes. And we know that these ontologies and external KBs are often well equipped to handle all the codes because they are designed for that task. Also, they have zero-shot support, which is not possible with multi-label classification. So yeah, in the end, I think I would just like to say, personally, I don't feel there is a best way to automate medical coding today, but it really depends on what you're looking for and what you want to optimize for. It could be speed. If speed is your number one concern, maybe you should go with multi-label classification. If it's accuracy, maybe NERL plus external KB might be the best approach. However, it could just be a custom or weighted function of all these different criterias, and you can define or design your own metric and then choose your approach. Having said that, these three are not the only approaches that are present today. People are experimenting hugely with automating medical coding. It's a very active field of research, both like in research and industry. A lot of companies are actually trying to solve it. So I'll just touch base upon some of the future directions of AI in medical coding. Starting with hybrid systems. So I just talked about these three approaches in silos. However, we can often combine these three approaches and build hybrid systems. Then prompt learning and RAG is something that is very actively being explored today. There are architectures that can retrieve code descriptions from ontologies and quickly generate those codes. You don't even need to maintain extensive ontology and the hierarchies in your own systems. Then you can also have transfer learning and meta-learning approaches to tackle code set changes and rare codes. Also, one very interesting thing that is happening now is that a lot of these teams have humans in the loop for efficient feedback mechanisms because oftentimes the clinical nuance of medical coding gets lost when we use any of these methods. So a lot of people are now trying to have some form of human feedback into the loop to make it more efficient and to make the feedback faster. Talking about healthcare data in general, we know that it's supposed to be private, and there are a lot of things that you need to do to ensure that whatever systems you're building are safe. So there are a lot of ontology-aware models and federated learning approaches that are also being explored to preserve privacy and handle the evolving standards of these codes. Additionally, multi-domain datasets and multilingual datasets are also being used to improve generalizability across contexts because we know people write those codes in different ways and there are different domains. So radiology is just one domain, primary healthcare is another domain. So the codes, everything could be very differently, right? And you don't want to be maintaining different pipelines for different domains. So it's really helpful to build a system that can generalize across different domains, different languages, and different contexts. So yeah, that's it for my talk today. I hope it was useful for some of you. And yeah, you can also go through some of the resources that I have mentioned here. These papers, I think the two papers here are really useful. At least they helped me a lot when I was doing my literature review for some of the work that I did in medical coding. And of course, if you want to explore some of the libraries or the ontologies, I have added links to them as well. Yeah, that's all from me. Thank you so much.
Thank you, Reyha. So it's time for questions. Please feel free to ask the questions you have to the speaker. We have a first question there.
Hi, so first, thank you so much for an amazing presentation. It was really insightful. Can we come back to the slide where you introduced the third approach? And I just wanted to ask on the high level, really, the next one, so where you have this, in a way, link of the steps, what goes after. Yes, exactly. So we're having no text, we're having all those steps, and which are the ones that require our input in terms of building, building the data set, building the, basically building some kind of structure. Because, for example, no text makes sense. It's basically what we would fit to the network, right? But when it comes to the ontology graph, I'm wondering whether it's generated from node texts data set or whether it's something separate that we have.
Right. That's a fair point, and thanks for the question. So there is no one model that sits here, to be honest. So when I talk about NER, there could be multiple NER pipelines that you can run, right? First, you extract the entities, you try to find relationship between those entities, and for that, you use this ontology graph, which is an external graph. So it has nothing to do with that particular node text. Right? So this is almost like the world knowledge of medical domain that exists in the world, and then you're trying to use that to find the relationship between the entities that were found in your node text. So there's no one model that you are training here. That is what we do in approach 1. And that has its own limitations, but it's easier to implement because you can just give in data and expect like some predictable codes. But here, since you're using all the world knowledge, it's very hard to essentially retrieve the correct relations between the the graph and your node entities. It's hard to do that back mapping, but that is what also makes this very accurate. So yeah, so there's no one model. You could implement NER in different ways. There could be multiple NER models. There could be multiple systems that run under the hood, but there's no one single model here.
Thank you. So essentially, ontology graph is in a way like the knowledge from the domain that we can either infer from something. So we're not compiling it, like we're not creating it ourselves. We can kind of use some, well, not pre-trained, but basically like we can take this graph from somewhere else, right?
Yeah, that's true. So you can have some names. You might need to do similarity matching because we know when doctors write or when you convert an entity, it might not be an exact match what you find in the DB or the ontology. So you might have to do some form of similarity matching. For that, you might need to spin up vector DBs and save your data there. Have a copy of that DB in a vector database. So there are different approaches you can take to solve that efficiently, but yes, so it's almost like you are using some world knowledge that doesn't exist in your system, and it's not yours, to be honest. Yeah.
Thank you so much for
Thank you.
answering.
Thank you. Do you have another? Yes, please go on.
Yeah, thank you for the presentation. I have a question for the F1 score. It's like, what's the best F1 score you obtain with the third approach, for example?
Yeah, I'm so sorry, I don't remember that on top of my head. Since I was working in a company and the metrics are really different there, and we used a lot of approaches to sort of increase the efficacy of the system, it was not only this, this approach. So we did a lot of things to additionally improve the score. So I can tell you it was definitely more than 93, but you might not get that with just implementing what I showed today. So, and of course it can vary. It really depends on how you implement the system. But it can be high. It can be high with approach 3 at least, because you get a lot of world knowledge from that ontology if you can use that efficiently.
Does it mean that the system can be deployed to help clinical coders or replace them, for example?
Yeah, so I think what it's trying to do is to sort of replace manual coders today. So hospitals also run short of that manual support. So I know of a few healthcare companies that exist in US who don't have enough people. So that is why they use this system. So I'm not saying they replace people. They also have people to review, because then there are 2 flows. So one flow is where you are very confident that whatever you predicted is right and you directly send it to the insurer. But there is the second flow where you know your system is not doing a good job and you want to send it for manual review. So that is where you send those codes to the manual coder sitting in the hospital to review and then send to insurers. So it's sort of helping them just do that final check and not look at everything. Basically, we say that whatever is simple enough or medium simple can be solved by this system, but what is really hard for a system to solve, there we still need human intervention and review. So that is how it's normally being done.
Thank you.
Do you have another question? It's the last one, please.
Thank you very much first for the very interesting talk. Can you comment on, do you know in Europe would such a tool fall under like the European Medical Device Regulations Act now, or can you actually implement this already because it's not directly impacting the patient outcome if you're using it like after the effect just to essentially bill the insurance company?
Right, thanks for that question. So I actually did not do a survey of how European market works, to be honest, with regards to this system. However, having said that, I know that there is an equivalent system of getting insurance money from whatever your policy is, and it might be transferable. I am not sure of that, and I don't know of a company that's doing that today. Essentially, the system, I feel, on a fundamental level, if you talk of implementation, it would be more or less the same, because I know that Europe also has standards. They have ontologies that you can use, maybe not UMLS, but some other codes. If it's not ICD, it has to be something else. So essentially, if you remove pieces and you replace them with like European standards, you would get like same accuracy, and the system should work as is. Because I don't see this to be a US-specific solution, to be honest. So yeah, I see that transferability, but yeah, I'll have to check a little deeper on how that the AI Act impacts it.
And maybe a second part if no one else is, if I'm not interrupting. Yeah, in your experience, when you implemented this in hospitals, was the biggest issue like data quality? Because I was working as a medical data scientist in a research hospital before, and we constantly had doctors coming asking us, yeah, they want to study something, but then we asked them, like, did you ever enter that data in the system? And they said, no. Okay, well then it's not in the database. So
yeah, I think this you almost have my answer, right? So I think a lot of times doctors don't write the codes correctly. Also, so basically the system has to integrate and get doctors' codes from somewhere. So this system called Epic and Athena that we normally integrate with. So firstly, the problem is doctors don't write everything. If they write it, it's not complete. And then you extract that text and information from some system, and you also have information loss there. Then whatever you get, you have to process and run these models, which are not perfect. And then in the end, using all these missing gaps, you predict something. So I think there's a lot of information loss that happens in the entire pipeline. So that could be, I think, number one, that there's information loss at every step. Second, I think also every healthcare system might need some rules. So they might have different ways of coding different things. So it's also really hard to build a system that is generic enough to be used for every healthcare provider. You often need to do a lot of changes, often need to take care of different things for a specific healthcare provider. That also adds a lot of overhead in terms of implementational effort. So yeah, that would be my top two, I guess.
Thank you.
Thanks.
Thank you, Reyha, for the amazing question. Let's give a round of applause for the speaker. So if you have more questions, please feel free to ask.